looking at chemical reactions. I'm your teacher, Pochulamba, who will take you through this lesson. So, I say we'll continue looking at chemical reactions. So, under chemical reactions, we've looked at the factors that affect the rate of a chemical reaction. Now, in today's lesson, our lesson focus will be on graphical representation. Graphical representation. So, in today's lesson, we are going to focus on graphical representation under chemical rates. Under chemical reactions, you can be given a question that is based on graphing, where you may be asked to come up with a curve. So, before you come up with a curve, there are some steps that you must follow for you to come up with a graph. So, one of the steps that you should do is on a graph, like the one that I have, and one of them which I have given you, like this one here, the Zambian Standard Graph paper, this one, you find that along this line, we have what we call the y-axis. Then along this line, we'll have the x-axis. So when we say you label the axis, that is what we mean. So the first thing you're saying, you have to label. You have to label the axis. That is the x-axis as well as the y-axis. Are we together? Yes. Now, based on the data set that you've been given, the coordinates, the points that you want to plot on the graph, you have to study the values that have been given for you to come up with a good scale. After you've labeled the axis, you look at the data that you've been given, the data set. Then after that, based on that data, you should come up with a scale. So the second thing that you are supposed to do is you make a scale. Make a scale. And this scale should be both for the y-axis and for the x-axis, based on the values that you've been given. Then, the third one is each graph in science must be given a title. There are so many graphs in science. So for you to give a clear picture to the marker, you must give the graph a title. So the third we are saying, you must give a title to that particular graph you are plotting. Then the fourth thing is, after you've given the graph a title, using the data set that you've been given, you should now start plotting the coordinates carefully. So we're saying the fourth one, you must plot the coordinates. You must plot the coordinates carefully. Then, the last thing, after you've plotted the coordinates carefully, you have to join those. You have to join the coordinates. So we are saying you join the coordinates with a smooth curve. On a graph, it is advised that you use a well-sharpened pencil. Then you should avoid what we call double lines. Then you should also avoid a thick curve, as we are going to illustrate on the graph board. Are we together? Yes. Okay, now, putting these steps into consideration, let's work out one problem based on graphical representation. We are going to have a problem, then we try to interpret it on the graph board. So we can take this example. So example number 1, zinc metal reacts with dilute hydrochloric acid. Dilute hydrochloric acid. The volume of the hydrogen gas produced is collected and measured in a gas cylinder. At different time interval, as illustrated in the table below. So here we'll have time, and this time is in seconds. Then here we'll have volume, and this volume is in cubic centimeters. So we start with 0. The time interval is being measured every after 10 seconds. So 10, 20, 30, 40, 50, 60, 70, the last one which is 8. So when time was 0, the volume for the gas collected was also 0. When time was 10 seconds, the volume collected was 15 cubic centimeters. When time was 20, the volume collected was 20 cubic centimeters. Then 33, 42, 47, 50, cubic centimeters, 50, and 50. So, we are given this as our data set. Then we are told to plot a graph of volume against time. Plot a graph of volume against time. So, what it means when we are told to plot a graph of volume against time, what we said, what we discussed was that we have to first label the axes. So we are now going to start using our graph board. So it is advised on that graph paper, on this graph paper that we use, it is advised, if you don't want, you leave one bigger box on your y-axis, you also leave another down there. Are we together there? Yes. So I'm going to be using this graph. So you find that this graph paper that you are using Along the y-axis, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This one has 13, but those which come from ECZ, they have 12. 12 against 10. Are we together? Yes. So, you leave at least one box. So, on your graph paper, we are going to be considering this as our bigger box, which is a 2 by 2. Are we together there? So, I'm going to leave one bigger box this side along the y-axis. Again, another bigger box this side along the x-axis. We are together? Yes. So, we are saying that the first thing we are supposed to do is to label the axes. So I'm going to label the y and the x-axis. I will begin from this point. So I say this is my y-axis. Then along this, again I draw. And I will say this is my x-axis. At the end of the x-axis here, I am putting this arrow. Then that's when I put the x. This arrow simply indicates that numbers are infinite. Same applies along the y-axis. You indicate the arrow and the y-axis, simply meaning numbers are infinite. They can go on and on. Are we together there? From there, so this is our y-axis. This is our x-axis. Now we get back to our table. We want to come up with the scale. Are we together? Okay. So now we look at time, which is along the x-axis. So what is the biggest number that has been given along the x-axis?
80.
Yes, George? 80. Yes. So the biggest number that we have along the x-axis is 80. So now, when coming up with the scale, okay, along the x-axis, since we've been given 80, it will not be a difficult task to do. Because you should think, because a graph should cover at least 3/4 of the graph, right? Okay. What we mean is this. This is your graph here. Your graph should not be squinted on one side. At least it should cover, along the x-axis, it should end somewhere there. And along the y-axis, it should end somewhere there. That's what we say, it should cover at least 3/4 of the graph. Not whereby you will have a graph, all this part, you don't use it, you just come and do your KVA. You just plot your KVA. No. It should cover about 3/4. Are we together there? Yes. Okay. So, since what we have along the x-axis is 80, so you should start thinking on how we are going to manipulate this graph. So, to say, okay, since they are saying I should at least use 3/4 of the graph. So from this point, at least it ends somewhere there. It should cover more than half. At least going beyond this point, going this side. Are we together there? Okay. So if this is your origin, this is your zero, this is where you're beginning. How many boxes can you leave so that at least it covers 3/4 of the graph? Yes, Dresden? 10. 10. According to Dresden, people are saying 10. So now, if you are using 80, then you leave 10 boxes. The thing is, you try to avoid working with decimal points on the graph because it will confuse you. So the best you can do is to at least you leave 8 boxes, 8 bigger boxes. So you're going to say, okay, I'm going to leave how many bigger boxes? 8. So this is 1, 2, 3, 4, 5, 6, 7, 8. So you put your 8 there. Are we together? So when you put your 8 there, how many boxes have you left? Yes, Mbalika?
8 boxes.
You've left 8 boxes, right? Okay. You've left it. So now, what we are doing is, we are trying to come up with a scale. So this scale, along the x-axis, what is the biggest number that we have? The biggest number that we have is 80. How many boxes have we left on our graph there? We have left 8. So 80 divided by 8. This is going to give you 1. What does it mean? What it means that on your graph, this box, which is a 2 by 2 there, represents what? Represents 1 unit. Now, along the x-axis, we said we label the axis. So along the x-axis here, what we are finding is what? Is time, and this time is what? Is in seconds. So it means that along the x-axis, 2 centimeters represents 1 second. Oh, sorry. It represents 10 seconds. It represents 10 seconds. So when we begin to count, we are going to start with this 0 because this is our origin. So from 0 you add 10. What are you going to get?
10.
We get 10. To this 10 again we add another 10. 20, 30, 40, 50, 60, 70, and what? 80. Because this is the last. So, along the x-axis, 2 centimeters represents 10 seconds. So for you now to know the value of a smaller box, you divide this 10 by the number of those smaller boxes. And the number of smaller boxes from our graph, from there to there, you find that there are 10 smaller boxes there. So for you to know the value of this smaller box, you simply divide this 10 by the number of boxes, which are 10. Are we together? Yes. Okay. Again, we go to the y-axis. Along the y-axis, what is the biggest number which we have? John Nirongo.
50.
So along the y-axis, so now we are making the scale for the y-axis. So what we have, the biggest value we have is 50. So you should start thinking to say, how many boxes should I leave? So now that's why we come now to breast mass. So yes, 10. How many boxes can we leave?
10 boxes.
10 boxes. According to them, we say you leave 10 boxes. 10 bigger boxes. So, what does that mean? What it means is, we are going to count from our graph. From there, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are ending there, and this is where we're doing what? We are putting our 50. Are we together? Then what did we say? Along this, what is there? What is there is what? Is volume. And this volume is in what? Is in cubic centimeters. So what we are saying is our biggest value is 50. How many boxes have we left there? We've left 10 boxes, right? So we're going to say 50, which is the biggest value, divided by 10. What is it giving us? Deborah? It is giving us 5. So what does it mean? It means that along the y-axis, 2 centimeters represents 5 cubic centimeters. Are we together? Okay. So 2 centimeters represents 5 cubic centimeters. Then, after we've come up with the scale, this, you write this on the graph. Which part on the graph should you write this information? You write it in the top corner there. Have you seen? Mostly we write it there because it is the graph, it is very impossible for the graph to reach this part. You can't write it at the middle because your graph, your curve might pass there and it will distort your results. No wonder we put it in the top corner there. So really write our scale based on what we found there. So scale x-axis. So on the x-axis, 2 centimeters represents 10 seconds. Then on the y-axis, 2 centimeters represents 5 cubic centimeters. When we've done that, we said each graph must have what? Must have a title. So what will be the title of this graph? Miracle. So our last value 50 is there. You can't write your title there because definitely your graph will pass there. So you write it on top there. So the name of this graph is a volume against. It's a volume against time graph. Are we together there? Yes. So this is the title of our graph. After we've done this, you've come up with the scale. Everything is there. What is now missing is the curve. So now we start plotting the coordinates carefully on the what? On the graph. Are we together? Yes. So what is our, sorry, we've forgotten. Okay. According to our y-axis, we are saying 2 centimeters represents 5 i. So from there, we start adding going up by 5 i. Yes. So 0 plus 5. 5 plus 5. 10 plus 5. 15 plus 5. 20 plus 5. 25 plus 5. 30 plus 5. 35 plus 5. 40 plus 5. 45 plus 5. 50. Which is there. So, after we've done that, we now start plotting the coordinates carefully on the what? On the graph. So, we start with our first coordinate. What is our first coordinate? Yes? So our first coordinate is 0, 0, meaning they are at the origin line. So we simply you indicate by putting a small cross with a sharp pencil. Are we together? Our next coordinate is 10. When time is 10 seconds, the volume of the gas produced is what? 13. So now, on your graph, there are these smaller boxes. So here we are going to put imaginary boxes. Imaginary small boxes. So there are smaller boxes. How many of them? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, if this is our 10, from there to there, from this point to this, the 2 centimeters represents 5 cubic centimeters. So for us to know the value of this smaller box, we have to divide this 5 by 10, which gives us 5 divided by 10. Yes, President? 0.5. 0.5, meaning the value of a smaller box is 0.5. Now, which value are we looking for? We are looking for when time is 13, meaning along this line, the volume produced was what? 18. So we start here. So this is 10, 10.5, 11.0, 11.5, 12.0, 12.5, 13. So we extrapolate a line. It comes this side. Where this and this are meeting, there, that is where our coordinate is supposed to be. Are we together? Yes. What is our next coordinate? Our next coordinate is when time is 20, the volume produced is 25. So 20, our volume is this one, 20.25. This one is this because 25 is there. So you come like this, where the two are meeting, which is there. That is where the coordinate is. Are we together there? What is our next coordinate? Our next coordinate is when time is 30, the volume produced is what? 33. But we know that the smaller value, the value of a smaller box along the 2 by 2 there, that smaller box inside there represents 0.5. So when we count from 30, this is 30.5, 31, 31.5, 32, 32.5, 33. So from there, you extrapolate a line, or you put your ruler there on that line. On the graph, it is visible on the line. But we are using imaginary lines. When time was 30, the volume produced was 33. So our coordinate is simply there. Then, when time was 40, what was the volume produced? So when time was 40, the volume produced was 42. So our 40 along the x-axis is there. So along this line, this is where time is 40. Now we go to the y-axis to look for the value, which is 42. So we have our 40 there. So 40, we count how many boxes? Smaller boxes. We count 4 of them. This is 40.5, 41, 41.5, 42. Are we together? So from there, again, we extrapolate a line, dotted line. Our 40 is there, along this line. So here, where these two are meeting, that is where our coordinate is. Our next coordinate is when time was 50 seconds. What was the volume produced? 47. So 45 along the y-axis is there. 50 is there. So along this line, this is where time is 50 seconds. Now we come this side. We count. This is 45. Well, our imaginary line is 45.5, 46, 46.5, 47. From there, we put this ruler, our ruler there, and put some dotted lines. So it's 50.47. Where the two are meeting, which is there, we put our small cross there. Are we together? So we are done up to the E. Our next is when time is 60. So we go up there. What was the value of the volume produced along the y-axis? 50. So 50 is there. So when time is 60, the volume produced was what? 50. So when you come like this, the coordinate is simply there. Are we together? What is our next coordinate? Our next coordinate is when time was 70 seconds, the volume produced again was what? 50. So 70, the 50 is there, we're coming this side, so our coordinate will be at this point. Then the last one is when time was 80, again, the volume produced was 50, meaning the reaction has come to an end. Time is moving, but the volume that is being collected is not changing, meaning the reaction has come to an end. So we've to join. The last thing that we're supposed to do now is to join these coordinates carefully. You are going to use your free hand. You don't have to use a ruler to join these points. You just use your free hand, and you must use a sharp pencil. So from there we join. So I'm starting with this one. I come with this, and you don't have to stop. So, I have joined my coordinates. I have joined all the coordinates that I have plotted on the graph. So now, some people might be wondering, as we are starting, we said we have to avoid double lines. There are some of you, look at my point there, it has not come out nicely. So, maybe I want to redo it, to join. I come again. I'm joining this and this. I join like that. So you find that I'm able to see two lines there. These are what are known as double lines. These are discouraged on the graph. So if you done like that, you have to ensure that you use a clean eraser. You erase the one that you don't want. So you erase it like that. Even this one, you erase so that it is no longer there on your graph. Then the other thing that we are supposed to avoid is using coming up with a very thick curve. Some of us just there want to do what? To go again. You are more like shading. So you find that the way the curve is looking, going this side, from this point going this side, and from that point going that side, and in between them, they are different. This one, which is in between, is very thick, and this one is also discouraged. Any question? Any question?
So sir, is there always on the exercises?
Okay, when it comes to graphing, always time is along the x-axis. So at times, all the data points given, they can do it at times to confuse you. They can change. They can bring the volume there, and they can bring time there, then they also change the values like that. So with you are not supposed to get confused. Always, time should be along the x-axis. Then the other that remains should be along the y-axis. Are we together? Any more questions? Yes, George.
So, sir, what more is the coordinates of decimal numbers?
If the coordinates of decimal numbers, you can manipulate the graph. That's what we call manipulating the graph. So how do we manipulate the graph? Okay. For example, along the volume, maybe along the volume, the biggest number or the biggest value that we are given is 19.5. Maybe the volume, the last figure along volume is 19.5, 19.5. For you to work out with this, the 19.5 will be very difficult for you. So the best is you manipulate it. How do we manipulate it? You round off this to the nearest 20. But it does not mean that the 20 will be plotted on the graph. It is this, meaning our graph only go up to 19.5. Okay, well class, we've come to the end of this lesson. How was your teacher, Pochibamba, on behalf of the production group? Thank you very much. Until we meet next time. Bye.